So, now to end this module, we will look at again some aspects of colloidal interactions, and we have seen several types of colloidal interactions in the bulk, van der Waals interactions, electrostatic interactions, steric interactions, and other. And we saw that the colloidal interactions at the interfaces in general are modified when compared to corresponding interactions in the bulk. As an example of that, we found that we discussed that in the case of a charged particle, the electrical double layer around a charged particle is symmetric, and however, when the particles are at the interface, because of the fact that the dissociation only happens in the region of the particle surface that is in contact with one of the phases, depending upon the nature of the dissociable groups, we know that the electrostatic interactions, instead of being proportional to e power minus kappa times the separation distance, they go as 1 over d cube, right. So, this is an example where the electrical double layer interactions are at the interface are modified when compared to corresponding interactions in the bulk. And similarly, the same would also hold, although we have not discussed, same would also hold good for the van der Waals interactions as well, because we know that the permittivity of the medium in which the particles are placed dictate the magnitude of the Hammacher constant, and hence the magnitude of the van der Waals force of interaction. Now that the particle is part in the oil phase or the air phase and part in the water phase, it will see different fluids, that means different permittivities across the interface, and therefore the van der Waals interactions will also be modified when the particles are at the interfaces. So, although certain interactions will get modified when the particles are at the interface, there are certain additional interactions that arise when the particles are at the interface, and these interactions are typically are not present, or they are absent when we consider particles in the bulk. And these an example of these interactions are what are called as interface mediated interactions or capillary interactions. Okay. And before we talk about these interactions, I would like to point out to one of the assumption that we have used in the calculation of the interfacial position and the detachment energies, is that the interface is flat. That means the interface is unperturbed by the presence of the particle. However, that need not be the case. If you have the assumption that the presence of the particle at the interface does not deform the interface will hold good only for a weightless particle, or when the particles are very small. So, what you are looking at is two cases. One is reference state, and that shows the equilibrium configuration of a weightless particle. That is the case where the gravitational forces on the particle can be neglected, and if we have the radius of the particle is r, and that is related to the radius of the contact line and sine of the contact angle by this expression. And now when you have, so that's this is for a weightless particle, right, the configuration A. Now in B, what we have is a particle when the interface is deformed. Okay. So, that is the dotted line that you see, that is the equilibrium, that is the location of the interface when we had a weightless particle. Now, we have a force F, that is the gravitational force that is acting on the particle, and that is pulling the particle down, and because of which the interface is deformed as shown by these lines. And what you also see in the figure is that there is this u of r that is that captures what is the magnitude of the interface deformation, and that is a function of r. And this delta h, it denotes what is the shift of the colloid center because of the gravitational forces that is acting on the particle, and r is the radial distance from the vertical axis of symmetry. That means, so that's the vertical so that is the vertical axis of symmetry that coincides with the center of the particle, and r is measured perpendicular to this vertical axis. Now, the extent of the shift in the particle position, that is delta h, and the size of the deformation, which is characterized by this u of r, it depends on a dimensional parameter epsilon f, which is defined as minus of f divided by 2 pi r times gamma naught, and gamma into r naught, where r naught is the radius of the contact line. This 2 pi r times gamma times r naught essentially gives us what is the surface tension force that is acting at the contact line, and F is the gravitational force. Okay. So, therefore, this EF is defined as the ratio of the vertical force that is acting on the colloid, that is weight minus buoyancy, and the denominator is the surface tension force that is acting at the contact line, right. When this epsilon f is very small, that means when the interfacial so when this quantity is very small, that means when the surface tension forces are dominant, then the interface deformation is given by the linearized Young-Laplace equation, and in this term there are two terms. This comes from the hydrostatic pressure contribution, and this comes from the Laplace pressure contribution, and so essentially one could solve this linearized Young's Laplace equation to find out the dependence of u of r with the radial distance r. Okay. And the solution of if we consider the interfacial deformation by a single particle, that means when there are no particles in the immediate vicinity of the particle, or for an isolated particle sitting at the interface, we can solve the linearized Young-Laplace equation to obtain u going as u naught times ln of lambda by r, where lambda is what is called as a capillary length, which is again defined as the ratio of the interfacial tension contribution to the gravitational contribution. Okay. And this has units of length, and typically for, if you look at water, oil or water air systems, this lambda would be typically of the order of millimeter. Okay. In such a case, u goes as u naught lambda ln of lambda by r when r is much less than lambda, and with u going as u naught going as minus r naught epsilon f and higher order terms. And for the case of r much lambda greater than lambda, u essentially the solution becomes of this form, and the vertical shift in lambda is minus 2 times r naught epsilon f. If you neglect higher order term, this u naught is minus r naught epsilon f, and giving which gives rise to delta h being minus 2 times r naught epsilon f. Therefore, if you know what is the gravitational force that is acting on the particle, and if you know what is the surface tension force and the radius of the contact line, we can actually estimate what is the shift in the particle position. And similar to the fact that the electrical double layer interactions originate when the interface the electrical double layer between the two adjacent particles overlap, when there is a overlap of the interface deformation, that is when the capillary interactions come into picture, and u capillary goes as minus 2 pi gamma, where gamma is the interfacial tension, r naught square, where r naught is the radius of the contact line, epsilon f square, which is the non-dimensional quantity that we define, which is the ratio of the gravitational force to the surface tension force times ln of lambda divided by d. Okay. So, therefore, one could estimate capillary interaction between the particles when they are sufficiently close such that there is a interface deformation overlap between the two particles. Now, the interface deformation we have discussed that the interface deformation can occur when the gravitational force acts on the particle. That is true for sufficiently big particles, typically of the order of 10 micrometer are larger. However, the interface deformation can also occur due to particle shape. What you are looking at is some results where what is shown is a interferometry experiments where the deformation around an elliptical particle and a spherical particle is shown, and so yellow region corresponds to a negative value of the position of the particle with respect to the interface, and positive value corresponds to the positive that means to say that when so if you look at the fact that if you look at this spherical particle case, no matter where we are around the particle, the interface deformation appears to be symmetric. That means in this case it is always a positive value of the z. That means the interface is in the case of spherical particles, the interface would either be elevated or depressed depending upon the nature of the particle that we are considering. However, if you look at spherical non-spherical particle, there is the interface deformation is, that means the value of the z is positive here and the value of the z is negative here. That means there could be interface elevations as well as depression around the particle when the particles are elliptical in shape. Okay. There have been experiments which capture the interface deformation that it is the interface is elevated in at the side and the interface is depressed at the edge of the ellipsoid, right. And such interface deformation are what are called as quadrupolar interface deformation, and these interface deformations have important implications in terms of the self assembly of such particles, whenever there is a interface elevation, that is typically referred to as a capillary negative charge, and whenever there is a interface depression, by convention it is referred to as capillary positive charge. And if you look at the nature of the self assembly of particles with such deformation, we see that there is always a tip-tip connection, either in different experiments, and that is because of the rule that the like capillary charges attract. Therefore, whenever you would see an assembly of particles with such quadrupolar symmetry, you will either see a tip-tip aggregation or a side-side aggregation, because these are the only two configurations that lead to the minimization of the total energy, free energy of the system, and the fact that the like capillary charges attract lead to such assemblies. In the case where the deformation of the interface is due to gravity is negligible, the distortion of the interface with respect to the planar condition, that is H, is it obeys the Laplace equation 2 dimension, and the solution of this Laplace equation is given by this, and the different terms that you see here are what are called as capillary poles. The first term is what is called a capillary monopole, the second term is what is called as a dipole, and the third one is what is called as a quadrupolar deformation, and we saw an example of that earlier. And the monopolar deformations are typically observed when we have a spherical particle at the interface. Also, this is an example where there is a pin that is located, that is positioned at the interface, and because of the weight of the gravity that is acting on the plane, you see that the interface is actually pulled up. Okay, and if you look at such monopolar deformation, as I mentioned earlier, there will either be interface elevation at a given r location, or there will be interface depression. However, in the case of dipole and higher order poles, you will have both elevation and depression around isolated particles. And these are examples where higher order poles have been observed. This is a case where there is a octopolar deformation, that is you have 8 regions, that is 1, 2, 3, 4, 5, 6, 7, 8, where there is interface elevation and depression occur around a particle. This is an example of again a quadrupolar deformation that occurs when you have elliptical and two-dimensional rod-like particles. Okay, so now going further, so the interface deformation can also occur in the case of when the particles are rough. That means if the particles are have some undulations on the surface, and these undulations can help in pinning of the contact line around the particle surface, and because of this roughness, the interface deformation need not be monopolar anymore, and there have been calculations which show that for a rough particle the interface deformation again is quadrupolar in nature. So would also be the case when we have particles with high surface charge. So what you are looking at is an example where we have a really large particle located at a water tetradentate interface, and what is plotted is the fact that the interface these image captures that the interface is not planar anymore, and we can actually calculate this angle psi, and it turns out to be 1.29 case where the particle is charged. However, when there is a sole effect of gravity, and this angle is given by 0.75. Therefore, so the difference between the two cases is that so 1.12.9 psi is observed when the particle is charged, as against 0.75 when the particle is deformed solely because of gravity. This additional deflection essentially comes from the fact that the particle is charged, and such the deformation are arising because of what is called the electrodipping force, that is, in addition to the force of gravity pulling the particle down, there could be contribution that come from the charge of the particle, and this also essentially gives rise to an additional deformation. Therefore, there are 4 different factors that can lead to the interface deformation. One is purely because of gravity that occurs when the particles are sufficiently large. Second, when we have a particle that is not a sphere, that is when the particles are non spherical in shape. We can either have a quadrupolar or octopolar or hexapolar deformation of the interface. We can also have interface deformation that arise because of the particle roughness and because of surface charge in the form of electrodipping force. So, just to conclude, so in this module we have looked at we started with discussing how to position particles at the interface. We looked at some applications of particle at interfaces concept in the form of using this for emulsion stabilization in the creation of new type of particles and new materials such as colloidosomes, and also their application in the making of porous materials as well. We looked at some additional characterization, how to obtain the equilibrium position of particles with respect to the interface. We discussed some important experimental observations which led to some hypothesis, followed by the development of theory for understanding the structure as well as the stability of particles and interfaces. And we show that we discussed that the surface energy balance calculations have important implications in terms of understanding the structure of monolayers containing these particles. We talked about calculation of energy of detachment, followed by how the interfaces, how the interactions are modified when the particles are interfaces. Finally, we discussed about interface deformation mediated interactions that arise only when the particles are at the interface, compared to the fact that the such interactions are absent when the particles are immersed in the bulk.